Alright. So quick announcement before we begin class. Friday's lecture will be on Zoom. Okay? I will send you the lecture link for the Zoom, to log into the Zoom. If you can make it, please do try to make it. I will be recording the lecture and I will be posting it on Carmen as well. Okay? Great times to be alive. It's not looking pretty tomorrow. Okay? Alright, so for today I'm going to start with a problem which is in some ways going to help you with your homework assignment as well. And it also solves the issue of tackling a problem in radial systems. Okay? I have the general heat diffusion equation. We discussed this last time. So for a constant thermal conductivity K by r to the power n d by dr of r to the power n dt by dr plus q dot. This is rho times c dt by dt. Okay, this is the most general form of the heat diffusion equation. When n is equal to 0, we get the plane wall, where you typically substitute r is equal to x. When n is equal to 1, you get the cylinder. When n is equal to 2, you get the sphere. Okay? Our focus for today is on cylindrical systems. Okay, so for us, n is equal to 1. And I also discussed the symmetry boundary conditions for a solid cylinder last time. We will go over that as we solve a problem today. Okay? So I'll set up a problem for us. In this problem, we have a solid cylinder. Okay, I'm going to call that a cylinder 1. So this is 1. So 1 is a solid cylinder. And the radius of the cylinder is 0.1 meters. Okay, so I'm going to call it as r is equal to r1 is 0.1 meters. This is r1. This cylinder is covered by another annular shell, which is typically made of insulation material. Okay, so I'm going to have that around this guy. Okay, and let's call that as cylinder number 2. So that's 2. And I'm going to draw the cross-sectional view of this. Okay, so I'm going to have the solid cylinder which is there in the center, approximately. This is cylinder 1. Then I'm going to have this annular ring that is surrounding the solid cylinder. Okay, so that's cylinder 2. Radius of the first one is r1, radius of the second one is r2. So starting from the center, r1, r2. R1 is already given to us as 0.1, so this is R1, and R2, 0.15, okay? For the solid cylinder, you're given a thermal conductivity, and this is equal to 250 watts per meter Kelvin, so K1 is given to me. And K2 is going to be a slightly lesser thermal conductivity, which signifies that this is some kind of an insulating material. So that's 5 watts per meter Kelvin. And then the outer ring or the outer shell is surrounded by ambient fluid. So there is ambient fluid here, T infinity and H. Okay, so if you want, you can draw it in the cross-sectional view as well. There is ambient fluid, T infinity and H. And the following information is given to us. So I'm going to maybe write that down here. T infinity is given to us as 18 degrees Celsius. The temperature of the outermost ring at R is equal to R2 is given to us as 25 degrees Celsius. So T at R is equal to R2. Is 25 degrees Celsius. Okay. The thermal, the coefficient of convective heat transfer is not known. H is not known. What are the things we need to do in this problem? We need to sketch the temperature profile after calculating the actual temperature profile with the data given. Okay, so obtain and sketch T as a function of R for the solid and the hollow cylinder, okay, or the insulating ring that is outside, different thermal conductivities, and also obtain the value of H. Given the fact that the solid cylinder has a certain amount of heat generation taking place. Okay, so Q dot is given to us, I believe, 50 kilowatts per meter cube. Just clarify that. 50 kilowatts per meter cube for the solid cylinder only. So Q dot only within the solid cylinder. Which means that the Q dot for the ring is 0. There is no heat generation taking place within the ring. So this is probably you can think of an application. This could be the core of a nuclear reactor where there is a large amount of energy that is being generated. It's very hot. You want to prevent the temperature of the core from declining, going beyond below a certain critical value, and so you surround it with insulation. You're asked to calculate what the temperature profile is. And you're also asked to find out, okay, if it is surrounded by ambient fluid, highly unlikely you're going to have nuclear coolant there. But typically if you have ambient fluid, what is going to be the value of H? Okay? So these are the things we need to find out. And maybe just a note here, no Q dot for the cylinder labeled 2, which is the hollow ring, okay, which encapsulates cylinder 1. Okay. So in this problem, unknown to us, there are certain boundary conditions that are available to us, which we need to siphon out and see, okay, how are these things going to help us in solving the problem. But before I solve the problem, here is what I typically do. It's a problem on one-dimensional conduction, which means that we start off with the heat diffusion equation. I handle the solid cylinder separately. I handle the thin ring separately. I'll call the temperature profile through the solid cylinder as T1 of R, temperature profile through the hollow ring as T2 of R. Okay? So say, we start off with the solid cylinder. T1 of R. This is going to be the temperature profile where the range of the radius is going to be so the radius starts at R is equal to 0 at the center line, and then all the way up till the outermost edge of this solid cylinder, I'm going to have the radius R is equal to R1, which is 0.1 meters. Okay? What are the assumptions here? That's all we're doing anyways. Steady state. Once again, I want to make sure everybody understands what steady state is. Steady state means that the rate of change of the stored energy is zero. This does not imply there is no heat generation. Could be having heat generation, but the rate of change of the stored energy is zero. Q dot is no longer zero for me. That's not an assumption, that's actually given to me in the problem statement. There is no information on radiation, so I'm going to ignore radiation. So these are my assumptions. With these assumptions, using the fact that the n is equal to 1, I set up the heat diffusion equation, integrate it twice, get the temperature profile in terms of some constants, which we did last class, but I'm going to do it again very quickly. I'm going to say that the thermal conductivity is K1. Okay, so I have K1 and constant thermal conductivity. That's another assumption that you're making here. Okay. Q dot is a constant value. So K1 by R. I'll start off with the original one. D by dr or dt by dr plus Q dot. This is your heat diffusion equation for a cylinder. Okay, one dimensional. The direction of heat transfer is radial. It is assumed that is the case because that is the equation that we have derived it from. There is no need to say that again. Steady state. So this is 0. Rearrange things there. So I have K1 by R, d by dr, or dt by dr, plus Q dot is equal to 0. Bring the Q dot to the other side. This is minus Q dot. Cross multiply. So that's d by dr or dt by dr Q dot r by K1. Integrate once, integrate twice, I get the slope, I get the temperature profile. Okay, so integrate once. R dt by dr. The d by dr term vanishes because I do the integration on the left hand side with respect to dr. On the right hand side I have a linear function of r, so it becomes a quadratic. So this is minus Q dot r square. 2K1 picks up a constant as we follow along. Okay, we did this last time. Integrate it one more time, but before you do that, divide through by r. And so I have the following. Integrate one more time. Before I do that, dt by dr is Q dot r by 2K1 C1 by r. This is with respect to a random radius r, where the range of r is from 0 to r. Okay. Integrate it one more time. T of r. Since I call it as T1, I'm going to write the subscript T1 everywhere, so pardon me on that. This is T1, T1, this is T1. Okay, so T1 of R I end up getting as the following. Minus Q dot R square 4K1 C1 times natural logarithm of R plus C2. What are the units for the natural logarithm? So ln r, logarithm of r, what are the units? Is dimensionless. Okay, so this does not have a unit, which means that C1 is going to be in degrees Celsius or Kelvin. C2 is also going to be in degrees Celsius or Kelvin, depending on what you're operating in. Okay? So this is one, equation 1. Set it aside. This is for a range of R for that particular range. Then I'm going to look at the thin ring. I'm going to call the temperature profile through that as T2 of R, T2 as a function of R. For a range of R from 0.1 to 0.15, which is from R1 to R2. Okay, so here for me, this is the range, less than or equal to, because it starts from R1 and then goes off to R2, so this is a bounded range of radii here. What are the assumptions? 1D, steady state, so similar assumptions, ignore radiation. And we will get to radiation, don't worry. So we will not necessarily start ignoring it once we know how to handle radiation in general, which is really quite painful, I'll tell you. Okay. Then we have a couple more assumptions from there. Constant K2. But of course we have to be thankful to radiation. We get our source of energy from there, primary source of energy. So something positive to understand, I think. Alright, and then Q dot is 0 for this situation. So E dot stored is 0 because of steady state. And given Q dot is 0 for this case. Once again start off with the HDE, general HDE. K2 by R, D by dr, R times dT2 by dr, because second temperature we are looking at. This is plus K dot, Q dot is rho C, dT2 by dt. This is supposed to be a T1 here. Cancel off. Cancel off. Q dot is 0, steady state, and so I end up with the formula. So K2 by R, d by dr of R, dt2 by dr is 0. K2 is a constant. I can take those quantities K2 divided by R, bring them onto the side of the 0, so I can essentially get rid of them without any loss of generality. Integrate once, integrate twice. So I end up here. Is equal to 0. So R times dt by dr, if I do the first integration, it becomes a constant because I have 0 on the right hand side. That is a different constant from the C1 and the C2 that we evaluated previously, or which we haven't done yet, but they are different obviously, because the material is different. Okay, and then the heat generation is also different in this situation, so the constants will not be the same. So dt by dr is C3 by R, cross multiply, integrated one more time. This is all T2, apologies. So the T2 is the following. Is C3 logarithm of R plus C4. Equation 2. Once again, logarithm of R does not have any units associated with that quantity, so C3 is going to be in degrees Celsius or Kelvin. C4 is also going to be in degrees Celsius or Kelvin. That's our expectation. Okay? In the homework, if you encounter a problem of this sort, unless I specifically ask you to derive the temperature profiles, just cite what we have done in the lecture today. Okay, but I will be asking you to do it in certain problems, for certain problems. So for that, you have to show me all these steps that we have done here. Otherwise, just take what we've done in class. Okay, beautiful. Boundary conditions. First question to you, how many unknowns do we have? How many unknowns? 4. So 5. Very nice. I have 5 unknowns. If I don't know H, I don't know anything about this problem, really. So C1, C2, C3, C4, and H. Okay, so I have 5 unknowns. I need 5 boundary conditions of some sort. So we expect or 5 equations. I shouldn't say boundary conditions, but 5 equations. Alright, so we start off with a solid cylinder. We discussed this last time. For a solid cylinder, T1 minus Q dot C1 logarithm R plus C2. We said that if I substitute R is equal to 0 here, at R is equal to 0, the temperature at R is equal to 0 is physically a quantity that is present. It is a physically measurable quantity. But if I substitute R is equal to 0 in the expression for T1 of R, I see that there is logarithm of 0, which makes the situation completely unphysical. So to have a physical answer, because that is fact of life, cannot change it, the quantity C1 should end up being 0. Okay? So for a physical answer, T1 at R is equal to 0, we need C1 is equal to 0, and this is equivalent to saying that for a solid cylinder, if I take the first derivative, so this is minus Q dot R by 2 K1 plus C1 by R, and C1 is 0, and at R is equal to 0, we will see that the slope is 0. So solid cylinder only. Okay, this is called as the symmetric boundary condition. We discussed this last time. So this is the first boundary condition. So if you see a solid cylinder, your first boundary condition is dt by dr at R is equal to 0 is 0. Okay. Which implies that C1 is 0, so we have obtained the first constant. So I'm done with C1. I need 4 more conditions. Yes, question.
For C1 over R, the permissible 0.
No, so you will typically pre-multiply by R throughout.
Oh, yep.
Yeah, okay. It's all just mathematical tricks, that's all it is. It is physically not possible to have a temperature that is unphysical at the center line. So we have to have that C1 is equal to C. Yes, question.
Could you set the temperature at R1 equals temperature at R2 along with the slope as a boundary condition?
Very nice, very nice. That's actually my next step. Okay? So we are in search of 4 more boundary conditions, right? So you've given me the second boundary condition. So this is the first one. Second boundary condition, obviously temperature is a continuous quantity, there is no discontinuity for us. So the temperature of the material with the thermal conductivity K1 at R is equal to R1. So T1 at R is equal to R1 has to be equal to T2 at R is equal to R1. The temperature value has to be continuous, the slope need not be continuous. That depends upon the material that you have and the thermal conductivity there. Okay? So this is the second boundary condition. Let's make use of this boundary condition. So first of all, what we have, based upon what we found out, C1 is 0, so T1 of R is minus Q dot R square 4K1 plus C2. This is T1 of R. T2 of R is just whatever we just did some time back. C3 ln R C4. So I am making use of the second boundary condition. Perform this substitution. Okay? So T1 at R is equal to R1 is minus Q dot R1 square 4K1 plus C2. So we've done the substitution. This is equal to C3 ln R1 plus C4. I'm going to call this as equation 4, this is equation 3. This is equation 4. Okay. Obviously this is completely useless because I don't know C3, I don't know C4. So obviously I don't know C2. But we shouldn't lose hope, we should continue. Two more boundary conditions. Here is what we need to do. At the interface, R is equal to R1, I can perform a surface energy balance. Okay, which means that if I perform a surface energy balance, my volume is approximately 0, so I do not have any volumetric effects considered. So the energy stored, the rate of change of that is 0. The energy generation rate is 0 as well. Okay, so at R is equal to R1, surface energy balance, which implies E dot stored is 0, E dot G is 0. This is irrespective of the fact that there is energy generation in the solid cylinder. That's something to keep in mind. Okay, if you're doing a surface energy balance, energy in is equal to energy out. That's it. So I draw a control surface. Let me first draw solid. This is the ring, so I draw my control surface at the interface between the solid and the ring. Okay, so this is my control surface. It is there is great suspicion that the heat transfer is obviously going to take place from the center here all the way through to the radius R1 and then to the radius R2, because I know that the temperature at whatever R2 is 25 degrees, temperature outside is 18 degrees, heat can only travel in one direction. Okay, so we can say that this is the rate of conductive heat transfer, so Q conduction at R1 for the material K1. So somehow I'm going to have a subscript there and I'll draw it out here too. This is Q conduction K2 at R1. That's energy in, this is energy out, so Q conduction for material K1 is Q conduction for the material K2 at the same radius R is equal to R1. Can everybody read my writing? People in the back and the sides? All good? Okay. Subscripts are fine. This is conduction, because there is also convection taking place in this problem, not within the body. Why is there no convection within the body? There is no bulk motion. That's the only reason. Okay. And then this is Q conduction, comma K2. The area of heat transfer is the same because I'm at the same interface, so I can essentially say that this is the flux. Okay. So if you want, you can call it as A at R1. A at R1. Write these as the flux, watts per meter square, cancel off the areas, and so I have the following. Minus K1 dt1 by dr at R is equal to R1 is minus K2 at R is equal to R1. Before we go ahead, obviously the negative sign vanishes, okay, so I can say this is plus, this is also plus. I'm just preempting what the nature of the slope could be, what the slope discontinuity could be at R is equal to R1. So you see this is the slope as I go through the material of thermal conductivity K1 at R is equal to R1. This is the slope at R is equal to R1 as I enter the material of thermal conductivity K2. You will see the discontinuity here. dt2 by dr at R is equal to R1 is K1 by K2 times dt1 by dr at R is equal to R1. K1 is higher than K2. K1 is 250. K2 is something 5. So the slope at R is equal to R1 is greater than since K1 by K2 is greater than 1. Does this make sense to everybody? This will help me draw the temperature profile. I will notice that as I go from R is equal to 0 to R1, I'm going to go in a certain manner. I'm going to have a slope, but then there's going to be slope discontinuity taking place. The temperature value is still the same. That's from this second boundary condition. Okay? Alright, continuing. So that's the equation. Well, we haven't done the equation yet. Now I go through the math and then substitute dt by dr at R1 and R2 for T1 and T2. So K1 dt1 by dr is somewhere here. So T1 is that creature there, so that's minus Q dot times R1 by 2K1 after doing the substitutions. R is equal to R1. This is equal to K2 times C3 by R1, which is the differentiation of logarithm of R is 1 by R. Okay? So I've directly performed the substitutions. K1 is known, K2 is known, R1 is known, Q dot is known, so I can calculate C3. And my value for C3 is minus 50 degrees Celsius. We know this guy, this is known, this is known, this is known, and R1 is also known. Okay? Fourth equation. First equation, center line is insulated. dt by dr at R is equal to 0 is 0. So we made use of that. Then I made use of the fact that T at R1 and T2 and T1 at R1 is the same. Then we made use of the fact that there is energy balance taking place. What do you think I should be doing next? Yes.
T2 at R equals 2 equals 25 degrees Celsius.
Absolutely. I am already given the temperature at R2, so why not substitute, right? So T2 at R is equal to R2 is 25. This is given. Notice, if I don't have radiation, it does not matter what units I use for the temperature. I can solve the problem in Kelvin or I can solve it in degrees Celsius. If radiation becomes a factor, I cannot do that because of the nonlinearity of the temperature difference between the surrounding and the surface. Okay? So in this problem I can just deal with Celsius. Don't need to convert everything. So substitute. So C3 logarithm of R2 plus C4 is 25 degrees Celsius. R2 is known, 0.15 meters. Substitute. Solve for C4. Ends up with a negative sign as well. That's minus 69.9 degrees Celsius. I said this is some equation 6. That was equation 5. So my next logical step is, because I know C3, because I know C4, I can directly substitute and find out C2. Okay? So substitute into 4, equation 4. So solve for C2. Substitute for C3 and C4 into equation 4 that is written above. And if I do that, and I'll have all these steps outlined when I post my solutions on Carmen, so we don't want to spend time doing substitutions here. So C2, should C2 be positive or negative without solving for anything? Just by looking at that guy, looking at these values, you don't even need to look at the values, just look at that equation and imagine you have a solid cylinder. The outer ring at R2 is the temperature of 25 degrees, the ambient is 18 degrees, heat transfer is taking place from the solid ring onto the shell and then onto the ambient. So what should the temperature at the center line be? Is it positive or negative? Has to be positive, physically speaking. And when I substitute R is equal to 0, I end up getting the temperature at T1 is C2. So C2 has to be positive. Okay, these are all things that you can use to check and see if your solution is really correct or not, if it makes physical sense. Okay, so C2 is a positive value, which is some number 45.64 degrees Celsius. Alright, so all the constants have been obtained. This is the boundary condition. I should label it. This is the fourth boundary condition. This is the third boundary condition. Not to confuse with the equation numbers. Okay. In the last boundary condition, I need to calculate the convective heat transfer coefficient so I can perform a surface energy balance at the outermost ring. The surface energy at R is equal to R2. When you do surface energy balance, E dot stored and E dot generated is 0. Which implies E dot in is equal to E dot out. Draw my control surface. I need to see these steps. If you're doing a surface energy balance, you draw a control surface and you show me what's going in and what's coming out. Okay? So something like this, I need to draw something like that for the outer ring as well. Let me do that here. That's the solid, I'm not interested in it anymore. I have ambient conditions, T infinity. There is conductive heat transfer taking place into the control surface. This is at the radius r is equal to r2, so this is Q conduction. For the material of thermal conductivity K2 at R2, okay, and I'll rewrite it again so it is more clear. This is radial heat transfer, so the heat transfer is taking place in the radial direction along the radial lines. This is Q convection at R2. And with your permission, I'm going to get rid of this panel here. Everybody got it? Okay. So Q convection is equal to Q conduction K2 at R2. Surface area for heat transfer is the same because I'm looking at the same ring here. So I can say this is conductive flux and convective flux. And for reference, what should be the area A2? 2 pi R2 times L. And so you see, cleverly they did not give you any information regarding the length of the cylinder because it makes no difference to our life. At least for this problem. For certain problems it does. Okay? And substitute. Convective heat flux coming from the temperature T2 at R2 onto the ambient. So this is H T2 at R2 minus T infinity. Be careful, the conductive heat flux has a negative sign, so minus K2 dT2 by dr at R2. Alright, and do the substitution. So H T2 at R2 is already known to me, so that's 25 degrees. I don't need to go through and do the substitution. T infinity is 18 degrees, that's given to me as well. This is minus K2 C3 by R2, which is the differentiation of the temperature T2. Okay, solve for H. Ends up being 238 something. What are the things I'm particular about? I'm particular about the units. If you make a mistake there, you're not my friend. If you make a mistake in calculating H, you get it as 241.8. I don't give a damn, because these are all anyway made up numbers. But when you actually go to engineering problems, when you start working or when you do research, you have to start worrying about the numbers as well. What we're doing here is we're just getting used to the ideas. We're getting used to the concepts. Okay? Alright, so we're done with all of this. I need to draw the temperature profile. And I have a lot of good information available for us. I'm going to draw it out here. Now this is where the problem is more interesting. This is R. T is a function of R. I start at R is equal to 0. I have a block from R to 0 to R1. R is equal to R1. Obviously between R1 and R2 the difference is not this large. It's a very small gap, 0.05 meters, but it's okay for the sake of drawing it out. Temperature at R is equal to 0 is the highest. So that's going to be the highest point in my code. Okay? So this is obvious here. So if you want, you can do the substitutions. T1 at R is equal to 0 is essentially C2, which is something that we calculated, 45.6 something. Okay. How do I start off at R is equal to 0? What's the slope?
0.
Has to be 0 because the center line is insulated. We just came up with that first boundary condition. So my slope is 0 here. I have volumetric energy generation, constant. Because of the fact that I'm looking at a solid cylinder, I don't need to worry about the logarithmic terms. So this is just going to be a quadratic profile. And since the temperature at R1 is less than the temperature at R is equal to 0, I have to come in a parabolic fashion in the following manner. Okay, so this is going to be my profile, 0 slope, negative slope here. So this is T1 as a function of R. How do I start off? And this is for the material of thermal conductivity K1. This is for material of thermal conductivity K2. How do I start base question?
Question. So we know that's parabolic just from the first equation we got, T1 having an R squared term.
Correct.
Okay.
Correct. Absolutely. So I think it was there somewhere. And also because of the fact that the logarithmic term is vanishing in this problem for the solid cylinder. Okay? So the logarithm is going to have a certain curvature of its own. It's not going to have an influence on this profile. Alright. My next question is this. As I enter the material K2, what do you know about the slope at the entry R is equal to R1 into the material K2? Is the slope higher or lesser? We just derived it some time back. If you look at your notes, dt2 at R1 is greater than dt1 at R1, and you can do the substitutions and figure it out because you have all the constants anyways. Okay, so which means that the slope is much more sharper here as I enter the second material of thermal conductivity K2. Now the question is, do I go concave or convex? And it's fairly straightforward. Just calculate the slope at R is equal to R2. Because the radius is higher, your slope is going to be C3 divided by R, and so the slope there is going to be lower than at R is equal to R1, so this is going to be a lower slope. And so the manner of going is nonlinear because it's a logarithmic decrement. So I go in this particular manner. There is a slope discontinuity here. This is the slope as I enter the material K2, and this was the slope as I exited the material K1. The temperature is still continuous. I cannot have two different temperature values at the same point. Okay, this is not an unsteady problem, and even in such a situation that is kind of impossible. So this is slope discontinuity.